In this part of the chapter now, we'll talk about periodic properties. And periodic properties are certain trends that you will see in a periodic table. And this is more true for the main group elements, which is the S block and the P block. They have a certain trend in them. The D block, which is the transition metals, and the lanthanides, actinides, F block, they don't follow these trends. So this is only for the S and the P block, which is also called the main group elements. We learned back in chapter 2 that the first periodic table that was designed was actually made according to atomic weight, but that did not seem to follow certain trends, so Mendeleev rearranged it according to atomic numbers, and because of that he was able to see that certain elements in groups had the same kind of chemical properties, and so which means that there were certain trends in periodic tables. These trends occur in rows and groups of the periodic table and are called periodicity. The three main trends that we are going to study in this chapter are atomic radii, ionization energy, and electron affinity. These are all based on effective nuclear charge. This is the basic concept, effective nuclear charge. Once we understand what this is, then you can understand how we can determine the trend of atomic radii, ionization energy, etc. So first we will talk about what is effective nuclear charge. Effective nuclear charge, which is represented by ZEFF, it is the attraction of the negative electrons to the positive nucleus. The positive nucleus meaning the positive protons that are actually in the nucleus. The neutrons don't have any effect because neutrons are not charged. So they don't take part in this attraction over here. It's the negative electrons and the positive protons in the nucleus. Almost all the periodic trends, as we said, are based on the effective nuclear charge. So what is the trend? As the electrons are added to the same shell, the effective nuclear charge increases. Okay, now remember, effective nuclear charge is the attraction of negative to positive. As the electrons are added to a shell farther away from the nucleus, the effective nuclear charge decreases. So let's look at this little periodic table here and see the numbers. Okay, you can see the numbers also, for example, like in lithium, 1.26, and then neon is 2.52. And as we go across the row, these numbers are increasing. All right. On the other hand, the effective nuclear charge, the trend as you go down is not so much. Okay, so for example, going from lithium to neon has been almost a 1.3 increase, whereas going from lithium to sodium, it's a very small increase, which means the effective nuclear charge does not increase that much. So this is how we explain this. As we are going from hydrogen to sodium, each electron that is being added, so from hydrogen, which is 1s electrons, to lithium, which is 2s electron, the 2s electrons is going in a new shell. And then we have the 3s in sodium, and that is going into another new shell. So which means that as we go from hydrogen to lithium to sodium, we keep increasing the shells, going from n is equal to 1 to 2 to 3. And because the shell number is increasing, it is also getting farther away from the nucleus. If it is getting farther away from the nucleus, the attraction is less and less from the negative and positive. However, if you go across the row, going from sodium to argon, each of these electrons are being added to the same shell. If they're adding to the same shell, then the protons will have a larger attraction to all these electrons because all of them are close to it, not farther away as if you were adding a new shell, but it's in the same shell, so therefore the attraction between electrons and protons get a lot more. And this is what we call effective nuclear charge. So here are the trends again that we are going to talk about, and here are the definitions also of each of these. Atomic radii is half the distance between two nuclei. Now we say this is half the distance between two nuclei because the atomic size is very small. We measure atomic sizes in angstrom, which is 10 to the negative 10 meters. 10 to the negative 9 meters is nanometers. 10 to the negative 10 is angstrom. So it's a very, very small size, okay, for atoms. So we measure the distance between two nuclei instead of a radii actually from nucleus to the last shell. Ionization energy is the amount of energy required to remove one electron from an atom in gas phase. Electron affinity is the measure of energy change when electron is added to the valence shell. So if the energy is negative, that means an anion is formed. If it is positive, it means a cation is formed. Cation meaning actually electron is given away. And then there is metallic character. Metallic character usually does not come under periodicity as such, but I put it over here because you can actually predict the metallic nature of an element. Remember, metals conduct electricity and heat, they're malleable, and we'll talk about more properties later also. So the first trend that we're going to look at now is the atomic radii. Again, atomic radii is half the distance between two nuclei. So remember the effective nuclear charge. Effective nuclear charge increased as you went across and decreased as you went down. So if it is increasing as you're going across, it means that the attraction between protons and electrons is increasing. If the attractions between protons and electrons is increasing, the electrons are getting closer to the nuclei. If they're getting closer to the nuclei, then the size of the atom is decreasing, and that's the trend that you see over here. So in each of these rows, so for lithium, for example, you can see how the size is decreasing, and then for sodium row over here, size again is decreasing as you go across. On the other hand, if you're going down the group, then the atomic size is increasing, and that's because going from one row to another row, you have added one shell. Okay, so shell number 1 to shell number 2 to 3 and 4. So if you increase the number of shell, obviously you increase the size of the atom. That same trend is seen everywhere. Now remember, these are trends. You don't have to know the exact numbers for all of these atomic radii. All you need to know is the trend, okay, which means that atomic radii decreases as you go across and increases as you go down, which is true for all of these rows and groups. Here is a nice little graph for showing the atomic radii. Starting from hydrogen to helium, going down, the size is getting smaller. Then it gets larger because you added a new shell. Goes down, 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 up to neon then. And again, it increases because with sodium, you added another shell. Again, electrons are added to the same shell. Effective nuclear charge increases, so atomic radii decreases. And then boom, here again, increases because we added a new shell. So you see the trend going on and on like that. Now let's talk about ionization energy. Ionization energy is the energy required to remove one electron from an atom in a gas phase. Now we say this is gas phase because this removes the energy required to change a substance from solid to liquid and from liquid to gas, okay, because all of these elements, they may exist in different forms. Each of them may have a different melting point. So we get all of these elements in gas phase, and then you measure what the ionization energy is. And it is the energy required to remove one electron. And usually you remove this one electron from the valence shell, okay, from the outermost shell. So we're not talking about the innermost. So you start from the outer, and then you work your way to inside. So ionization energy increases as you go across, because remember, the effective nuclear charge is increasing as you go across because the attraction between electrons and protons is increasing as you go across a row. So if you go across a row and the attraction is increasing between electrons and protons, it gets harder and harder to remove an electron. Okay, so the ionization increases as you go across. But as you go down, the ionization energy decreases because the effective nuclear charge is decreasing. The attraction between the nucleus and the electron is not that much, so by the time you get to francinium, it is really easy to remove an electron from the outermost shell. Here is the trend for ionization energy, a nice little graph here. So between hydrogen and helium, yet again then, so helium has higher ionization energy because it's harder to remove an electron from helium than hydrogen. Then low for lithium. It is easy to remove an electron from lithium because now you're getting farther away from the nucleus, okay, but then ionization energy increases as you get to neon, and then again it decreases as you get to sodium because now you've added another shell. So here at the bottom, you will see all the group 1 elements, okay, because here the energy decreases, okay, as we go over here because the electrons are getting farther and farther and farther away from the nucleus, okay. So lithium starts at about 500 and then cesium is lower than 500, okay, by the time you get here. However, within a row, the ionization energy increases, decreases again as you start a new row, and then back again. This is a little bit of a different graph, okay, because now here I wanted to look at the ionization energy trends of not just one electron, but also of more electrons, okay, because ionization energy is removing one electron at a time, okay. So for example, hydrogen has only one electron to remove. Helium, on the other hand, has two electrons to remove. So it is easier to remove the first electron from helium than the second one. Why? Why is it easier to remove the first one? It is easier to remove the first one because the effective nuclear charge for the first one is not as much as it would be for the second one. By the time you get to that one electron is actually being pulled by two protons, whereas in the first ionization energy, you had two electrons and two protons. And so the effective nuclear charge for the second ionization energy is way more than the first one. And so therefore it takes a lot more energy to remove the second electron. For lithium, the first ionization energy, very less, 520. And then look, it goes really high. Why? Because now you're going into the second shell, okay, and trying to remove this electron that was actually for helium. And again, the effective nuclear charge is increased because now you have three protons, but only two electrons, okay. So the effective nuclear charge is a lot more. So the second new ionization energy for helium was still less than the second one for lithium because of the different number of protons in here. Now for these trends, I don't want you to remember the number. I need you to understand the logic behind where these numbers are coming from and truly understand the meaning of the effective nuclear charge, because that's what these numbers exhibit, okay. So when you get to beryllium, the first ionization energy is low, it gets higher because now remember, as you're removing electrons, the effective nuclear charge is going to increase because the protons are still the same. The number of electrons are less and therefore effective nuclear charge increases. Okay, and so by the time you get to the second, third, and fourth ionization energies, there is a huge difference. Okay, they keep increasing and increasing. So that's the trend that you will see for all of these elements here. Now let's look at the last trend, which is the electron affinity. Electron affinity is the measure of energy released when an electron is added to the valence shell of an atom. The amount of energy released, meaning that if more energy is released, the more stable an atom will get. Okay, or it is easier to add an electron if a high amount of energy is released. And as you can see, the trend is that if you go from left to right, okay, within a row, then the energy released is much higher as you go to the right than to the left, which means that it is harder to add electrons for the metals than it is for the non-metals. Okay, so the energy released, the higher the energy released, the better the electron affinity, okay, or the more the electron affinity. As you go down a group, the electron affinity decreases, and you can see that for everything, which means that it is harder to add an electron as you go down. It is easier to add an electron as you go across. That is the trend for electron affinity. Metallic character. Now, some of the properties of any kind of a metal is that they are shiny, they are malleable, they're good conductors of heat and electricity. They have low ionization energy, which means it's easy to remove electrons from the valence shell. They form ionic compounds. They form basic ionic compounds with oxygen also. And we'll talk about this basic property, okay, in a few minutes also. And the trend is that the metallic character increases from top to bottom. Okay, so if you go down a group, the metallic character increases, and it decreases as you go from left towards the right of a periodic table. These are the properties of nonmetals, and in case of nonmetals, everything is opposite of the metals, which means they're not in any way defined by color. They are brittle, they are poor conductors of electricity and heat. In case where metals will form basic oxides, non-metals form acidic oxides. Metals have low ionization energy, whereas non-metals have high electron affinity, which means they tend to form more anions. And then group number 7 and 8, which is halogens and noble gases, those are your true non-metals, which means there are absolutely no metals in those two groups. And then we have the in-betweens, which are the metalloids, and you know that those are the staircase that goes down diagonally in the P block, and they have the properties of both metals and non-metals, and we will study that also in a few minutes. So here is a chart for you, which is all the trends in one table for you. So effective nuclear charge, again, this is the definition. It increases across a group and it decreases as you go down the group. Atomic radii, distance between two nuclei, it decreases as you go across the group, increases as you go down. Ionization energy, amount of energy required to eject an electron, remove an electron. It increases as you go across, decreases as you go down. Electron affinity, measure of energy released, increases as you go across, which means it's easier to gain electrons. It decreases as you go down, which means it's harder to add electrons. And then the metallic character decreases as you go across, increases as you go down a group. And then there is something which we call the ionic radii. And of course, since we form cations and anions, we have to talk a little bit about the comparison between atomic radii and ionic radii. Remember, when you form an ion, you have to gain or lose electrons. Cations have given electrons and anions have accepted electrons. Okay, and remember, cations are formed from metals, anions are formed from non-metals, which are the right-hand side of the periodic table. So in case of the cations, since electrons have been given away, now the number of protons are more than the number of electrons. So the effective nuclear charge increases. If it increases, then the cations will tend to have a smaller radii than the original atom. Okay, so for example, lithium cation is going to be smaller than the lithium atom. Same thing happens for sodium. Sodium ion will be smaller than the sodium atom because now you have more protons and electrons. Once you go to magnesium, the ion, the cation gets smaller because the number of protons are still the same, but now you lost 2 electrons, and with losing 2 electrons, the effective nuclear charge has increased. With aluminum, the radii gets even smaller. Okay, and as you go down, the atomic radii will still increase, although it is still the cationic radii will still increase, but it is still less than the atomic radii. All right, and then as you go across form the ionic radii for the cations, the size of the cation will decrease. The trend is opposite for anions because in case of anions, you're actually adding electrons, which means that the effective nuclear charge is getting less. So in this case, the gray one here is the size of the anion. So in any case, or in any of these elements, okay, where they have gained an electron, the size of the anion will increase. It will be higher than the size of the atom, okay, itself. And again, as you go down, the size of the anion increases. And again, the size of the anion is still more than the size of the atom. As we gain more electrons, the effective nuclear charge gets less and less, and therefore 1 electron does not cause so much of a change as 3 electrons would. Okay, so look at the trend from chlorine to sulfur to phosphorus. Phosphorus can gain up to 3 electrons, so the atomic radii, or the ionic radii for phosphorus is a lot more because it's gained 3 electrons, and now the effective nuclear charge cannot keep up with that. Okay, so the ions are different for cations and anions. In anions, the size increases. For cations, the cationic size Here is another chart, and you can keep this one handy or you can keep the other table handy, whichever one you prefer. And it has all your trends on one chart. Okay, so the atomic radii decreases. The nice thing about this chart that I like is, of course, the arrows also indicate that the size is decreasing. The cations, the size is decreasing, and the anions here, the anions is more. So phosphorus, for example, was 3, and then this anion size is also decreasing. Electron affinity is increasing, and so is the size of the arrow. So you can keep this chart handy if you want to, and this shows you all the trends that we have just talked about. Now let's look at some solved problems, okay, how you would get a problem in case of periodic trends. And so here is one. Refer to the periodic table and arrange the following elements in order of increasing atomic size. So bromine, selenium, and tellurium. So what you do is then you identify the elements from the periodic table and arrange them according to where they should be in the periodic table. Of course, you don't have to write this out. You can just look at the periodic table and then identify where these elements are. Now looking at this, you know that bromine should have a smaller size than selenium because it's going across, and then tellurium should have a larger size than selenium because it's going down. All right, so which means that tellurium is the largest one in size and bromine is the smallest one in size. Okay, so that is how you come up with the trend. And so bromine smaller than selenium, and then tellurium. Tellurium is the largest one. And then here is the ionization energy trend. Again, you identify where your elements are on the periodic table, and then you know, look at your trend, that as you go across, the ionization energy increases. As you go down, ionization energy decreases, which means that Sb, which is antimony, is going to have the lowest ionization energy, and bromine is going to have the highest ionization energy. There's your trend. Bromine has the highest ionization energy, and then antimony has the lowest ionization energy. Isoelectric elements and ions are two atoms or species, which could be cations, anions, atoms, whatever it is, but they have the same electronic configuration, which means that they have the same number of electrons, but they will have different nuclear charges because the number of protons are going to be different. So if you have an atom which is neutral, will have a certain number of protons, but if it's become an anion, then you'll have different number of electrons. Okay, so let's look at some isoelectric species here. So for example, oxygen, which is 2 minus, fluorine, which is 1 minus, and then neon, all of these three have the same number of electrons, which is 10. That's why they're called isoelectronic. All right, so same number of electrons, 10 electrons, but the number of protons are different. For oxygen, they have 8 protons, fluorine has 9, and then neon has 10 protons, which means that the effective nuclear charge for all of these three is going to be different. For oxygen, since you have 10 electrons and only 8 protons, the effective nuclear charge is not so much. But then for neon, which has 10 electrons and 10 protons, the effective nuclear charge is a lot more. Okay, so isoelectronic species are any kind of species which have the same number of electrons but different number of protons. So which means that the sizes, the atomic or the ionic size, is going to vary. And this is something to keep in mind when you answer some questions. Now let's look at some of the properties of groups. So far we've talked about trends, okay, where we had certain properties that we were studying very specifically and see how they actually increase and decrease in a group. But now we're going to talk about all the groups in general. So group number 1, for example, the alkali metal, okay, and then group number 2, which is the alkaline earth metal, group number 7, which is halogens, and so on. So individual groups. So first of all, group number 1 and 2 are all metals. Group number 7 and 8, halogens, and the noble gases, these are all non-metals without any question. Transition metals are all metals. You will not find any non-metals in there. Group 3, 4, 5, and 7, they have non-metals, metalloids, as well as metals. And we will look at that as we go on. A little bit about oxides that I want to mention to you, because this is the main thing that I ask you in case of the properties of groups, is that when you take any kind of a metal oxide, okay, so which means, for example, lithium oxide, sodium oxide, magnesium oxide, and then you dissolve them in water, they will end up giving bases, which means that sodium oxide will give sodium hydroxide, which is a base. All non-metals oxides will give you acids in water. So for example, if you take something like sulfur trioxide and you add that to water, it will give us sulfuric acid, which is H2SO4. All the non-metals will always give you acids. All the metals will always give you bases. And then there are some which are called amphoteric oxides, which can behave both like acids and bases then. Those are usually found in metalloids, by the way. So here are some equations for you that you need to remember. And this is typically something that I will ask you in an exam, okay, for sure, because it is important that you understand the different properties of metals and non-metals, okay, as it relates to water and acids and bases. So metal oxides, okay, are usually basic, and this is the reaction I was talking about. So if you have sodium oxide, you dissolve that in water, you get sodium hydroxide. Non-metals will give you acids, and this is the usual trend, okay. Amphoteric oxides, for example, are like aluminum, because aluminum is a metalloid. So if you dissolve it in acid, it behaves like a base. If you put it in base, it behaves like an acid. So those things are slightly different, but otherwise, if you have true metals, they will give you only bases. If you have non-metals, they will give you only acids. So let's start with group number one. Group number one is the alkali metals, and their electronic configuration is an S1. And NS1 meaning N is the principal quantum number and S is the last electron that you fill, and it's always going to be in the S1 orbital. So here are your group 1 elements: lithium, sodium, potassium, rubidium, and so on. Now remember, we don't put hydrogen over here because hydrogen is not a metal. So you will not find hydrogen when we talk about alkali metals. So first of all, alkali metals are all metals. The reactivity increases as you go down because remember, the metallic character also increases as you go down. You can never find alkali metals in their elemental state in nature, okay, which means that you cannot go out anywhere and find sodium or potassium. These things actually have to be isolated and stored in a very specific location in conditions because these are very reactive elements. Their oxides are always going to be M2O, which is Na2O or K2O, for example, because of course they give only one electron. The special containers that we talk about as far as storing them is that they have to be removed from air and water because these metals can start reacting with even air in general. So we can't even expose them to air. Okay, this is sodium. The first one here is lithium. And look at the inner side of lithium. It's nice and shiny and bright, but look at the outside. Okay, and that is because it has reacted with air. One of the interesting properties about alkali metals is that they are very, very soft. Okay, and very soft meaning that you can actually take sodium and you can chip off a sodium using your nail. I don't advise that, but you can take a spatula and you can just cut it through and it cuts just like butter. Okay, it's a very soft metal and almost all the metals are like that in group 1. Group number 2 are called the alkaline earth metals and their configuration is Ns2, and here are all your metals for group 2. These are also all metals starting from beryllium all the way to radium. These are all metals. The reactivity again increases as you go down. They're a little bit less reactive than group 1, okay, which means that you can still find them and store them easily. Okay, for example, you have dealt with magnesium in the lab already. You've been using magnesium ribbon for almost all your labs, and so you can see that it's not very hard to work with. Okay, so they're less reactive than group 1. Their oxides will form the formula of MO, and the reason I've given here oxides for you is because we talked about the fact that if you take metal oxides, you can form bases. Some of these metals will react with acids to form hydrogen gas, and Magnesium, for example, if you can put that in acid, which we've done that in the copper lab, you know that if you put magnesium in HCl, it will start giving off hydrogen gas. You already have seen what magnesium looked like, which is pretty much gray, shiny metal. All the other metals also kind of look like the same way. Okay, so here is calcium and here is strontium. Now we get into group number 3, which is the P block now. The first group in the P block, Ns2 and P1, that is for the valence shell. And we start with boron, go on to aluminum, gallium, indium, thallium, and so on. And the first element here is a non-metal now. The next one, aluminum, is a metalloid. All right, and it behaves more like a metal than a non-metal, although in some cases you will see that it can behave like a non-metal as well, but it's more called like a metalloid. All right, and then by the time you go down, further down the group, these are all going to be metals. And when we say they are metals, it means that they react with acid. Once they react with acid, it means that they are metals. Non-metals typically do not react with acids. Aluminum forms Al2O3 with oxygen, aluminum oxide, and it is an amphoteric oxide. I already gave you the equations in previous slides. And the other elements that we have in there are pretty much metals, and they can give 1 electron or 3 electrons. Okay, so boron looks like this, which is a non-metal, and therefore it doesn't really look anything like a metal. It's shiny, but it's not malleable, and it doesn't have the other properties. Gallium is pretty unique in a way because gallium has a very low melting point, and you can see that even if you hold it in your hand, gallium will start melting. Okay, and yes, this person is wearing gloves. Don't worry about that. Then we get to group 4. Group 4 is one of the most interesting ones because we have all sorts of elements in this. Okay, so we have the non-metal, which is the carbon, silicon, and germanium. These two are the metalloids, and then when you get to tin and lead, these are your typical metals. Okay, carbon is a non-metal which looks like this. Okay, nice, crystalline, looks nothing like a metal. Silicon, germanium look typically like metals would, gray, shiny, and then when you get to tin and lead, they are very typical metal looking, okay, as well. Lead and tin, both of these, they form +2 and +4 oxidation states, and we've talked about that before when we did nomenclature as well. The other trend that we see in group 4, because you have the metals and the non-metals in there, the non-metals and the metals in here, is that carbon with oxygen will get carbon dioxide, and the metalloids are also the same way, and these three end up giving acidic solutions, whereas the two at the bottom, which are metals, tin and lead, the oxides that they form are actually amphoteric. They're not even basic, but they're actually amphoteric. All right. So group 4, for that reason, is a very interesting group. The other part about group 4 that is very interesting is, of course, all the organic chemistry is all based on carbon. All right. So that is a very important element as far as chemistry is concerned. Group number 5, again in the P block, Ns2 and P3. It also has a whole series of non-metals, non-metal, then metalloid with arsenic and antimony. By the time you get to bismuth, pretty much a metal. Okay, so here are some of the properties, okay, that you will find, that arsenic, antimony, and bismuth. By the time you get down here, they're very crystalline-like. Okay, and this is antimony here, Sb. And it doesn't look like a metal, but it definitely is crystalline, which means it's shiny and has pointy edges and all that. Nitrogen, on the other hand, is very unique because nitrogen is a gas. Okay, all the other elements that we've been talking about so far, including carbon, those were all solids. But now we're actually getting into gases. So nitrogen is a gas. Phosphorus is a solid. Okay, and phosphorus actually exists as P4, just like nitrogen exists as N2. Phosphorus exists as P4. Then nitrogen and phosphorus will give you acids as their oxides. So NO2 will give HNO3, which is nitric acid, and then phosphorus will give phosphoric acid, or phosphorus oxide will give phosphoric acid. And then antimony oxides are amphoteric, bismuth oxides are basic. So that's the trend that you will see in this group. Group number 6, which is the oxygen group. Now the metallic nature is decreasing, okay, because we're getting more and more towards the right-hand side of the periodic table. So in group number 6, you really don't find any metal, okay, that much. Polonium is a metal, but we don't deal with polonium so much that, we don't really talk about it, okay, as much. But polonium is the only metal that you will find in group number 6. All the other ones are metals or metalloid, okay, which is tellurium. All of these are typically nonmetals, which means that they give acidic oxides and so on and so forth. Oxygen exists as O2, sulfur as S8. This is how they exist in nature. Okay, that's what it is. Sulfur looks like this, and as you can see that sulfur has no metallic look at all, and oxygen is a gas, okay, for that matter. By the time you get to selenium and then later on tellurium, then they start looking a little bit like metals, but they're really not metals. Now for group number 7. Group number 7 are the halogens, NS2, NP5, and here are all your halogens starting from fluorine, chlorine, and then going on to bromine and so on. So first of all, these are all nonmetals. Okay, the other thing about them is that these are all diatomic molecules. F2, Cl2, Br2, I2. There are no metals in this at all. Okay, so they all exist as diatomic molecules. They all gain one electron, as we know from forming compounds. The physical property is a very interesting thing for halogens. Okay, we start with gases for fluorine and chlorine. So both of these are gases. At the time you come to bromine, it is a liquid, and then iodine is a solid. Now you've dealt with bromine in one of the labs, and you've also dealt with iodine, and that's a solid. Okay, and this is what they look like. Fluorine is a colorless gas, and chlorine is kind of a greenish colored gas. All of the halogens, they will form acids. Okay, so for example, hydrofluoric acid, hydrochloric acid, hydrobromic acid, these are the binary acids that we have. No oxygen in them, but they are very good acids as well. Typically, you will not find these elements also in nature. They have to be made and then stored properly. And finally, the noble gases. Okay, noble gases are NS2 and P6. By the time you come to this group, the whole shell is filled up, okay, with electrons. So the noble gases, starting from helium, going on to neon, argon, krypton, xenon, and then radon. All of them are monoatomic because they don't need to bond with anything, all right? And we'll learn more about that in the next chapter as well. But they all exist by themselves. You can find these gases in nature. They don't have to be synthesized. Okay, so noble gases are found. Now, depending on what gas you're looking for, some of them may be in higher concentration than others. Helium, for example, is mined. Okay, you need to have helium. We use helium a lot in chemical reactions because it provides a nice inert atmosphere to work in. Besides, what would you do if you did not have helium balloons? I don't know. Okay, all the parties will be a bust. So in those cases, helium is one of the maximum used gas over here. Neon, not so much. Neon is used for the signs, as you know. Okay, neon signs are very common, and that's because these gases will give different colors, okay, with electric current. Argon is very popular too as a gas in chemical reactions because again it provides an inert atmosphere because they don't react with anything. Okay, so it's kind of nice to use these gases in case you don't want oxygen or water, okay, in your reaction systems. Krypton, xenon, and then radon. Radon is a very heavy gas, and radon is found underneath the earth, okay, which means it travels in rocks and crevices. Radon is a very toxic gas. It's a radioactive gas, and it is recommended that you test your houses for radon because it causes cancer, okay. Krypton, of course, we know because Superman came from here, so who doesn't know Krypton? But anyhow, all of these are gases. All of these are inert, which means they don't react with anything. And for most part, they have no commercial use as such. We have found uses for them, but otherwise, since they don't form any bond or anything, there is no real use for them. So finally, from this part of the chapter, you should know all your trends: effective nuclear charge, atomic radii, ionization energy, electron affinity, metallic character. Also should be able to compare ionic radii and tell me which one is larger, which one is smaller. You need to understand the concept of isoelectronic species and then know the acidic and basic oxides. The last portion that I covered regarding all the different groups, that is pretty much and a lot for your general knowledge. Okay, so you understand that some elements exist in nature, some don't, and how they exist, whether they're in gas form or they're in solid form, what is it and what do they look like. So it's a little bit for your general knowledge, but also as we go on later, you will understand why they behave the way they do and why they exist the way they do.